Hey there guys, it's me Larry, and today I'll be presenting the Module 2 project for the ECEN 2350 Digital Logic class here at CU Boulder. Today's project, a 5x5 bit sign multiplication circuit, presented by yours truly, Larry Manalo. Okay, just as mentioned, we do have a main goal of taking in two 5-bit 2's complement binary numbers and multiplying them to result in a 9-bit 2's complementary binary number. But we also have some additional goals, such as using the Verilog language, in particular the generate and for loop functions, to create the multiplier circuit and to display the resulting 9-bit 2's complement binary number in hexadecimal or binary coded decimal on the 7-segment display. Because that step could have been skipped by just displaying the 9-bit 2's complementary number on the SMD LEDs that are on the Altera board itself. These row of, they're not lit right now, but they're the green, they light up green when in use. And that could just be read off as a binary number, but for ease of use for the user, we could have implemented the 7-segment display just to read off the numbers directly. Okay. I do have a plan of attack on the way I approach this problem. I started by making a half adder circuit, and then went on to make a full adder circuit using those half adder circuits that I made, and then also making a multiplexer function, and then using the full adder and multiplexer functions, I then made a unsigned 5-bit multiplier circuit, and with that, I then added the logic to make that circuit work with a 2's complement input. Do excuse me, it's 4 in the morning. I'm a bit tired right now. And after that, the resulting from this step would have been a 9-bit 2's complement binary number, but then we further went through and converted that to hexadecimal representation on the 7-segment display. Okay. Before we take a look at these different blocks and how they're coded and what they look like, there's some things to note about the whole process of why I approach the problem this way. Okay, it's important to note that in 2's complement, at least, negative numbers would always have the most significant bit be 1. The leftmost bit in this case, or the bit with the highest value in the square brackets in the code, as we'll show later, will be equal to 1. So what we can do before actually multiplying anything is to check if the inputs are negative or not. And if they are negative, we could turn them into a positive number so that the multiplier circuit would work. So the way we would change a negative 2's complement to a positive 2's complement would basically to invert the bits and then add 1 to that resulting inverted number. Okay, and having checked and done that if needed, we can then pass it into the multiplier circuit as unsigned numbers, and it'll just work basically just like how the book displays it, without having to do any extra padding, and just for simplicity. So the resulting number is a 9-bit 2's complementary binary number that is positive. However, you'll never get a negative number out of that 5-bit unsigned multiplier circuit. So we need to do a little conditioning on that number depending on what the inputs were. So like we have 3 cases outlined here, such as if in the first case, if both of the inputs were positive, the resulting number from the multiplier circuit is correct since there are no negatives to deal with initially. Nothing was converted. We're all good to go. In case 2, one of the 5-bit inputs were negative. Okay. In that case, we have to do the 2's complement of that input that's negative before passing both numbers into the multiplier circuit. And then we have to do the 2's complement, negative 2's complement of the resulting number from the multiplier circuit, as we know that the number should be negative. Okay. And in case 3, if both of the inputs were negative, what would have been done is to do the 2's complement to make them both positive prior to passing them into the multiplier circuit. And the regular output from that multiplier circuit should be the overall answer, since intuitively at least, a negative number times a negative number is positive. Okay. And after having talked about those three cases and any extra conditioning that needs to be done, we can then convert that 9-bit 2's complementary binary number into a hexadecimal number to be displayed on the 7 segments. Okay, it's important to note that at least how in my code it has 10 bits because it does include the last carry of the ripple carry adder for the last stage. We'll talk more about that later. But it can basically be ignored by the rules of doing the 2's complement. Okay. So looking at the other 9 bits of the product, you could check for negativity by checking that 9th bit if it's a 1 or a 0 again. And before we can do any conversion to hexadecimal, if the number is negative, we have to do the 2's complement and make it a positive number. Okay. So we'll represent negative numbers on the board with a actual negative sign. So my code checked for that 9th bit to see if it was 1, and then went to the segment 6 of one of the LED segments and turned it on, basically, to make it look like a negative sign. And then we made that number positive through the 2's complement, and then we broke up the remaining 8 bits. So we have the 10th bit that you ignore, the 9th bit that is the sign bit in a sense, and then you have the other 8 bits, which is essentially the number. What I then did was break up the 8 bits into 2 groups of 4, a higher significant 4 and a lower significant 4, and then had a function that would check each of the bits and then relate that to which segments would turn on separate 7-segment displays. So one group of 4 would be represented on one of the 7-segment displays, while another group of 4 bits would be represented on another 7-segment display. And this makes sense because the lowest 4 bits would be 0 to 16 on a hexadecimal, while or the 16th, the 0 place, while the next group of 4 would be, again, 0 to 16, but it'll be 16 to the first place. Okay, and in order to make it so that actual stuff on the 7th segment would turn on, we had to make a truth table, and we had to make a Carnot map to create the functions for each segment in the SOP form. So here, exiting out of the PowerPoint temporarily, I could show you that I did make the truth table and I did make Carnot maps for each of the LEDs. It was a lot of work and it took a little extra time, but it was easier to debug my circuit in the end as I had readouts on the DE0 board in a number form that I could just read. Okay, and before talking about this critical path delay, let's actually look at the code and the different blocks and see how it all fits together like a puzzle. So I'm going to open these pictures now. We do have our half adder and our full adder circuit here in a graphical representation. So in our half adder up here, do notice that we have our exclusive OR gate for the sum result, and we have the AND gate for the carry, basically, or sum and propagate. So it takes in 2 inputs, A and B, 2 bits, and it outputs a sum and carry. If both bits are 1, we'll have a carry and a 0. Otherwise, you'll get a 1 and a 0, or a 0 and a 0 if A and B are both 0. And here's a functional block picture for this circuit. And using our half adder block, we then made the full adder. Just like in our textbook, it has 2 full adders and an OR gate that compares the carries from each of the individual half adders. So why the full adder is important is that it takes in 2 bits, but it also takes in a carry in bit, takes that into account for the math, and then results in a sum out, like our X, and then our carry out, just like our Y. Okay. So having made the half adder and full adder, we also had to make a multiplexer circuit. I'll show you why next, but let's talk about this a little bit first. We have our 2 input bits, A and B, and our output bit C, and we have a selector bit. And if the selector is high, then we select bit B for C, and if the selector is low, then A goes through and becomes C. It's basically a bit selector, a 2-to-1 selector. But having the half adders, the full adders, and the multiplexers, we can then make a 5 by 5 multiplier circuit. Okay, if you do have the digital logic book for this class, I was going to grab it, but it's nowhere near me right now, do excuse me. This is the multiplier circuit that's provided in the book, except we did add some extra stuff. So for example, you'll notice that each row has 5 full adders and 5 AND gates versus 4. And we did have to add this extra diagonal circuit so that it would actually create the correct number of bits as the result. It's the same type of process of ANDing the bits with each other and then making the partial fractions and feeding the previous partial fractions and last carry into the next one, onward and onward until you have the correct number of multiplications, basically, resulting in your product form. But again, we want a 9-bit 2's complement sign number versus here we have 10. We ignore the last carry because of 2's complement ruling. But I do keep it in the code until we chop it off at the very end. Now moving on to the code. We have our code for the half adder, which is basically gate implementation of the picture. We have the full adder, again a gate implementation using instances of the half adder circuit and then the OR gate. We then made the multiplexer circuit, which are the 2 ANDs with the non, the selector, and then the OR gate. Let's see. Simple to code for, very primitive way of coding in Verilog, I suppose, but it looks nice and it works. And then we have our multiply 5. This is where things get a little messy, so do excuse me. We have a counter variable, we have various wires. We had to set the initial carries to 0, just like in the textbook. These had to be initialized to 0. And going back to Quartus 2, we'll talk about these later. Basically, my code didn't work off the bat, and I had to make some changes. But instead of implementing another for loop to initialize these values, I did them separately. But the main for loop of the function is right here, in which it ANDs the bits of 1 with each of the bits of Q. So one of our inputs is M, and we're multiplying we're ANDing all the bits of M with one of the bits of Q. And in the picture, this is that statement. This is AND all the bits of M, one of the bits of Q. And we do it again for all the bits of Q. And you'll notice that in our code, we do have 1, 2, 3, 4, 5 AND statements. Okay? And also notice that we have our 1, 2, 3, 4 full adder statements right here. Each full adder takes in, well, the first adder is special, as it takes in 2 of the AND lines versus all the other full ripple carry adders. That's what these are. These are ripple carry adders. They take in the sum from the previous line and then the ANDing, except for this last full adder. Okay. And in our code, we show it right here. Except here you see we have these input 1, input 2, input 3, and input 4, which is basically this. And why I had to do that is because it's important to note that even though the sum of the previous ripple carry adder feeds into the next line, this first full adder gets ignored, while the last full adder gets fed a carry out from the previous line. So how I had it in my code before, I had the full adder feeding accordingly like that, but that wasn't correct and I was getting the wrong numbers. So I had to change my input to have the second full adder feed into the first 1 minus, and then have the last carry out feed into the last full adder in the next row. And that's basically what these input lines are. Okay? But having checked it, it does work, and I'll show you on the E0 board shortly. These assign statements are basically these bottom lines would say these values are equal to the various bits of the product for the 9-bit 2's complement product of the multiplication. Sorry about that, guys. The recorder that I was using has a 15-minute time limit, and unfortunately I already hit that. So this will be a part 2 in a sense. So having just gone through the 5x5 unsigned multiplier, we do have to add a little to it to make it so that it'll work with the 2's complement numbers, which is where this circuit comes in. Okay. Do note that our M and Q here are our two 5-bit 2's complementary binary inputs. And this circuit is just a little conditioning in case the number was negative or not. As discussed earlier, if the number was negative, we would take the invert of the bits and then add 1 to the whole number, which is basically what this does, because the highest bit, the most significant bit, is the data selector for the multiplexer as well as the carry-in. So if it was 1, it would select the inverts of the bits as well as be the carry-in, basically adding 1. Okay, same thing for Q, and having the conditioned numbers, we could then pass it to the multiplier, but depending on whether the inputs were negative or not, we might have to do a little conditioning with the output of the multiplier. This is where those 3 cases comes in, whether both were positive, one of the inputs was negative, or both of the inputs were negative. And that would be determined using this half adder and this multiplexer, in which if one of them was negative, C out, which is the AND gate of the half adder, would be 0, and S1 out would be 1, which basically do the invert and add 1, because negative times a positive number, or positive times a negative number, should be negative. If both of them were positive, C out would be 0, and S1 out would be 0. Basically leave the multiplier output the same. This does not do anything effective, and it makes sense because it's 2 positive numbers. And if both of these were high, meaning both the inputs were negative, C1 out would be 1, and S1 out would be 0. So pulling the 1, which is from the ground, again, we're not touching anything with the multiplier output because the negatives cancel out, and the positive number should be just fine. Okay, and looking at this from a code perspective, we got our 2's comp multiply. Sorry, excuse me here. We have our multiplexer and the full adders for each of the inputs M and Q, just like in the picture. So this is a multiplexer, and this is a full adder line, multiplexer line, full adder line. And then we pass it in to our multiply 5 circuit, which was the example for the textbook expanded a little bit. And then we talk about the multiplexer and the conditioning. So this multiplexer and half adder right here are the checking for the 3 cases. This multiplexer and half adder. And then the 2 other lines below that in the for loop was the extra conditioning, just like how we did with the inputs. Okay, so it follows the picture really well, simple clean code. Again, we're using the generated for loops, just like in the multiply 5 circuit. And that should output our 2's complement 9-bit binary number product. Okay. And having to do the conditioning again to turn that into a hexadecimal for the 7th segment, we have our 2's complement to hexadecimal here. So we did have to make a binary to hex that was based on the truth table from earlier. Right here, each segment, 0 to 6, has a SOP form function that corresponds to the various inputs for a 4-bit number from 0000 to 1111. And here we have a check for negative again, because if it's negative, we want to do the negative sign, and then find the magnitude of that number, which is basically invert the bits and add 1 again. And then we break it up into groups of 4, more significant 4 and less significant 4, and we would then display it on the corresponding LED segments. So the most significant would be on the left, the less significant would be on the right. And important to note that this is for the negative sign if needed. Since the LEDs are active low, by setting all the other segments to 1, essentially turns stuff off while letting the center segment 6 be the opposite of the sign bit, because if the sign bit was 1, we'll get an active low here, turning that on, meaning it's a negative number. Okay. So having shown how the code works, I guess it's time to actually show the board and do some example cases to prove that my function actually works here. So I do excuse the glare from the computer, but here I have all 10 switches on the off position, which basically means it is a 0 times 0, which is 0. And sorry if it's hard to see, but it is displaying 0 times 0. If I move all the bits, all the switches to the high position, that's the same as saying -1 times -1. And here you could see that this is 0, 1, and 1 times 16 to 0 is 1, and there you go, it works. Another test case we could do could be -1 times 1. -1 times 1 is -1. We have our negative, our 0 and 1. And we could also do like -1 times 2, -1 times 4, -1 times 8. You know, and it's basically the binary number on the right, just negative. And then we can also do -15. So notice here that we went into the letters of hexadecimal, and the F is 15, you know, 14. I move the 1 bit down, becomes the E, and I have all the various letters, and it's the same. That's D right there. That's our 9. All the letters are the same as the example code that's on the DE0 board when you first power it on. Again, this was made using the truth table and the Carnot maps. And I guess we could do some 2 positive number multiplication, such as 16 or 15 times 15. 15 times 15, which is the right 4 bits. As you can see here in the calculator, 15 times 15 is equal to 25. And what we're getting on our board when we do this multiplication is E1. E is basically 1 below F, so that's basically saying 14 times 16 plus our 1 from the ones place, getting our 225. So it does work for negative times negative, positive times positive, negative times positive. And I mean, feel free if you have any questions regarding the code and the board, please feel free to comment as well. Besides that, now that the code works and everything, one of the other things we need to talk about is the critical path delay. So the critical path delay is the longest path that the data needs to travel in regards to the whole processing of, or this function doing its thing. And this is regarded as the number of gates that it needs to travel through, and not this time. So starting with our smallest block, the half adder, it only has 1 block for each possible pathway. So it has a gate delay of 1. The full adder has a gate delay of 3, as you can go from one of the inputs to this sum through C2 through the OR gate. Okay. The multiplexer has a maximum of 3 gate delay because the selector has to go through an inverter, AND gate, and OR gate. Not always, but it's a worst case scenario. Okay. And the binary to hex converter, it's important to note that from our code, the binary to hex converter was a SOP form. So the worst case scenario is a NOT gate, an AND gate, and then an OR gate for one of the functions. Any one of the functions, actually. Meaning that I'll have a max 3 gate delay. Okay. And the multiplier circuit, this is where things got a little tricky, but I did notice that the maximum path, longest path, would be for the 9th bit of the product, because I'll have to go through this full adder, then this one, and then this one, and then this one, and then following the carry-ins, it'll go from this to this to this to that, and then an AND gate. So it'll be 1 AND gate and 1, 2, 3, 4, 5, 6, 7, 8 full adders, giving you a total of 25 gates. Okay, and then using the multiplier circuit and the other stuff, so we have any one of the longest paths with the 2's complement multiplier would be having to go through the NOT gate, multiplexer, full adder, multiplier circuit, another NOT gate, multiplier, multiplexer, and then full adder. So this situation would be when this input was negative, this was positive, causing this to have to go through as well, making that negative. Okay. And we calculated that to be a total of 39 gates. So overall, considering the 2's complement multiplier circuit and then the little blocks and converter needed to make the hexadecimal for the 7-segment display, we're talking a good 48 gate delay. And although the DE0 board may show, sorry, that's 0 times the number. So although the DE0 board shows almost instantaneous transition, in high speed or high frequency applications, this could be really significant. However, it's important to note that it was a relatively simple design because it used the basic full adders, and despite it being slow, in theory it does use less gates than using a more complicated adder, such as the carry look-ahead adder. Because since this is a 5-bit multiplier circuit, the 5th carry in a carry look-ahead adder would have 32 gates to it, 32 inputs. And that's something that's just not practical in real life. And it's going to just be really expensive. But it's expensive for speed. Time, took less time to code. Does take more time to process, but it uses less gates. And this was my approach to the Module 2 project, 5x5-bit signed multiplicator. If you do have any questions, please feel free to leave them in the comments, but thank you very much for listening in.